Hello everyone, today we're going to do chemistry topic 4, which is inorganic chemistry A level or AS level. So first we got group 2, we've got summary questions there as always. You don't have to do them now, you do them later, but this is just so you can have in mind what kind of questions you'll get. So first, trends. Down any group the atomic radius increases because there are more shells being added, so that's just common sense. So down group 2, the first ionization energy and the electronegativity will decrease. You should have done topic 1. If you haven't done topic 1 yet, then please go do it. I've made a video on that as well. Since group 2 metals react by losing electrons down the group, they will become more reactive. Since it's easier to lose electrons down the group. Down group 2, the melting point decreases because of the larger atomic radius, except for magnesium. The melting point decreases because they rely on their metallic bonds, but magnesium's got a different crystal structure or something, it just wants to be different. And this leads to less attraction between the metal ion nuclei and the delocalized electrons. That's what metallic bonding's made of. Got another graph there. And the solubility, down group 2, the solubility of hydroxides increases, metal hydroxides, while the solubility of sulfates and carbonates will decrease. An exception to the carbonates trend is strontium, but all of the group 2 carbonates are they're not very soluble. They're a tiny bit soluble, I guess. And you don't particularly need to know the reason, but the reason is as the lattice energy decreases, the solubility increases. That's just part of topic 8. And for small negative ions, the lattice enthalpy will fall faster than the hydration enthalpy. I'm not going to go into that, mainly because I don't know much about it. Reactions. So down the group, the reactivity increases because of the sum of the first and second ionization energy will decrease. Group 2 metals will react with water to form a metal hydroxide and hydrogen, but beryllium won't because it's really small and really unreactive. It won't react with water, otherwise it would be too unstable. And magnesium will do it very slowly because magnesium's the next smallest. But they'll react with steam to form white metal oxides, beryllium and magnesium, because steam's a lot hotter than water. That's a bit part of topic 8 too. Mg plus H2O creates MgO plus H2. Group 2 metals will react with air to form oxides quite readily. Mg plus O2 creates MgO, and if you heat them, they can also react with nitrogen to form nitrides, but you don't particularly need to know about that. Like other metals, they'll react with dilute acids to form a salt and hydrogen. That's not any different from transition metals. And down the group, the salts produced will be less soluble. So as I put that normal acid reaction, Mg plus H2SO4 creates MgSO4 plus H2. And group 2 oxides will react with water to form a metal hydroxide. MgO plus H2O creates MgOH2. These then dissolve and make the solution alkaline because of the OH2. And that's why alkaline metals, aren't they called? The summary questions. These are all past paper questions, by the way. 1. Explain how the trend in reactivity of group 2 elements is determined by their electronic configurations. That's 3 marks. And 2. A white solid was thought to be barium carbonate. Students suggested the presence of the carbonate ion could be tested for by adding a small amount of sulfuric acid. Explain whether or not the suggestion is valid. That's 2 marks. 1. The outer electrons are furthest from the nucleus. There is more shielding down the group, so the first ionization energy decreases and reactivity increases down the group. Oh, I forgot to tell you, you should pause if you want to answer them. And 2. Usually carbonates react with acids and produce gas, but barium sulfate produces insoluble, so the bubbles of gas aren't expected because of the ions and stuff. Groups 1 and 2. So first we've got thermal decomposition. When group 1 and 2 metal carbonates are heated, they produce a metal oxide plus carbon dioxide. For example, CaCO3 plus creates CaO plus CO2, and that's decomposition. You've got one starting reactant, and then that produces 2 or more reactants. It's like decomposition, and you heat it up as well. That's thermal. When group 1 nitrates are heated, they produce metal nitrite plus oxygen. 2KNO3 creates 2KNO2 plus O2. That's nitrite there. And then when group 2 nitrates are heated, they produce metal oxide plus nitrogen dioxide plus oxygen. That's the one you got to remember. MgNO3 creates MgO plus NO2 plus O2. Have I not written that? Well, whatever. Thermal stability is the resistance to thermal decomposition. A thermally stable compound, it won't decompose when it's heated. But group 1 and 2 carbonates and nitrates, they're not very thermally stable, but down the group they have higher thermal stability. That's because the charge density is lower. So charge density is the amount of charge per size, so the ionic radius becomes larger while the charge remains the same. So for example, if you've got a huge atom with 1 plus, that's not very charge dense. It's quite low charge density. If you've got a tiny atom and it's 5 plus or something, then that'll be a really high charge density. So that'll be less stable if it's attached to a carbonate, because carbonate's quite big. You can't see that. Not very stable. And that also affects polarization, which we'll look at in the next slide. The bonds in the carbonate ion, they're all identical, like in benzene. You might not have seen benzene before. You probably should have if you're doing A-level chemistry, but maybe you're doing the bare minimum. So that's benzene. So that circle there shows that all the electrons are delocalized, because the Kekulé structure is like that or something with the double bonds, but that's incorrect. And the carbonate ion bonds are kind of the same, except usually you will draw the Kekulé structure for that. Is that Kekulé structure for carbonate? I'm not sure. But yeah, with a double bond and then 2 bonds and O there. But in reality, that's more like a dashed bond is how you'd draw it, actually, if you want to be accurate. Remove that double bond if you're doing the dashes. And they're also more likely to be found around the oxygen atoms, again, topic 1. So that's electron clouds more drawn to here because they're more electronegatives. That's delta negative it would be. And when they bond to a group 1 or 2 metal, this electron cloud goes towards the metal ion. So you've got a metal here, for example, potassium, and all the electrons will want to shift towards here. That's the electron cloud now. And that's polarized, so that because this is 2 areas. This is where most of the electrons are, and over here it's got very few electrons, and so that also contributes to thermal decomposition. So if you heat it up here, that will break the bond here, and if it's got a high charge density, if it's really small, then it will become even more polarized, because the electrons will want to go here even more because there's fewer electrons here. So then that will just be way more unstable here, so you can just heat it a tiny bit and then it will decompose. You can see there KO and CO2. Quite a nice reaction, that. And when a carbonate ion bonds to 1 or 2 metal, yep, already said that. And the same concept can be applied to nitrate ions. That's exactly the same, nitrate and carbonate, except it's N. And if more polarized, less stable. Flame tests. That's carried out using a Bunsen burner on a blue flame, so that's so you can see the colour. And you've got to use a platinum or nichrome wire. Doesn't matter which one, platinum's more expensive but also more effective. And that's so that it doesn't affect the colour produced. And you use hydrochloric acid to remove residue between tests, if you don't want your old chemical to affect your new test. And the colour is produced because the heat causes the electrons to move up to empty orbitals at higher energy levels. So you've got your energy levels here, that's how they look. So you've got electrons here, and it gets heated up, so it will go up to a higher energy level because it's got more energy. But that's very unstable, so they'll quickly drop back down, and then that dropping back down, that releases a photon, which is light. That's quite physicsy. That have a specific frequency, which is the colour. And so you've got these colours, you just sit here and memorize them, I guess. And beryllium and magnesium, they like to say they have no colour, but actually they're white. And the reason for that is because the colour produced is outside the visible light spectrum, so you can't see it, but you would just see it as white. It's not like it's actually colourless. Summary questions. 1. Explain why group 1 carbonates are more thermally stable than group 2 carbonates. 3 marks. 2. Explain the origin of flame test colours. Explain how they happen. 4 marks. And 3. Which of the following ions does not give a red flame? Barium, calcium, lithium, or strontium? 3, 2, 1. 1. Group 2 has a larger charge density in general, and it polarizes bonds more effectively, therefore. So the CO bond will be weakened. 2. Energy/heat from the flame promotes/excites electrons to a higher energy level. They then drop down to a lower energy level, releasing photons/light. 3, barium, does not give a red flame. That's a green flame if I remember correctly. Halogens. Down the group of halogens, the boiling/melting points decrease. This is because they are joined by London forces. Again, topic 1. And they become stronger as the molecules become bigger because there's more electrons. The fluorine, chlorine, they're gas at room temperature pressure. Bromine's liquid at room temperature pressure. And iodine and below are solid at room temperature pressure. And down the group, the electron affinity down the group, the electron affinity increases, and the electron affinity increases, and the electronegativity decreases. They're the opposite of each other, because the outer shell is farther from the nucleus. Also, electron affinity is its ability to be attracted to electrons, and electronegativity is the ability to attract electrons. Halogens react by gaining electrons, so with lower electron affinity, they will be more reactive. Who wrote this? They'll be more reactive. I wrote this. And halogens nearer the top of the group will be better oxidizing agents, while halogens at the bottom of the group are better reducing agents. There's some random info you've got to remember. So in water, chlorine is green, bromine is orange, iodine is brown, but in cyclohexane, iodine is purple. I've never seen a question on this, I'm not sure you have to know it. ClO- is chlorate, ClO3- is chlorate 5. And NaClO is bleach. This is quite an important one to remember. It'll save you a lot of time in your exams. NaClO is bleach. And disproportionation, that's in topic 3, a reaction where one element is both oxidized and reduced. Right, reactions. If a light halogen is added to a heavy halide solution, so a light halogen is just up the group, it will be displaced because the up the group, the halogens are more reactive, so it will displace the heavier halogen. Displacement reaction, you should have done that in GCSE. Fluoride plus H2SO4 creates HF. That's a reaction with sort of halides with sulfuric acid, that's just the ions. Bromide plus H2SO4 creates bromine plus SO2, and chloride plus H2SO4 creates HCl, and iodide plus H2SO4, that creates a bunch of things, but this is the one you need to know, I2 plus H2S. And that's H2S, that's really toxic, poisonous, everything, smell like eggs, apparently. And of course, hydrogen halides are all acids like HCl, hydrochloric acid, and they'll all have those acid reactions like with carbonate ions, etc. And you should memorize this one. You can figure it out, but this is nice and easy to memorize rather. So Cl2 plus H2O, that's reversible, creates HCl plus HClO, and that's reversible, which can create further 2H plus ClO minus plus Cl minus. In sunlight, HClO will decompose into HCl plus O2, so the reaction won't continue to that, because obviously this is decomposed, so it can't do that. And this reaction is used for water treatment to kill pathogens, like say that, like cholera. And apparently some people will be like, oh, you shouldn't put chlorine in the water because that's could be dangerous, but it's probably more dangerous to put cholera in the water. So believe what you want, but this is what you've got to know for your exam. Qualitative analysis. We can use silver nitrate to determine which halide ion is present. So you've got a nice solution, and you've got some halide ions in there, but you don't know which ones. So you put that in, and then that's the equation is Ag plus X minus. X is a halogen or a halide ion, creates AgX, which is solid, which is a precipitation reaction. AgCl is white, AgBr is cream coloured, and AgI is light yellow. You probably won't be working with the other ones, they're a bit dangerous. And also you've got to put nitric acid in there to remove any carbonate ions, which would just interfere with that. And obviously use nitric acid, because you can't use hydrochloric acid because that's a halogen, that would be halide ions, false positive. And colours can be difficult to tell apart, so we'll add ammonia, and that will dissolve some of it. AgCl will dissolve, AgBr will slightly dissolve, and you've got to add a lot of ammonia for that, and AgI won't dissolve at all. Right, summary questions. 1. Bromine can be extracted from seawater containing bromide ions using chlorine. Write the ionic equation for that reaction. That's a nice easy one. 2. Predict the physical state of astatine under room temperature and pressure, and thus justify your answer. And this is all 1 mark. 3. Write the equation for the reaction of chlorine with cold dilute sodium hydroxide solution to form bleach. Right, I haven't taught you guys that reaction, but you should be able to figure it out. It's like the one with water. It's very similar. 1. Cl2 plus 2 Br minus creates Br2 plus 2 Cl minus. 2. Solid, that's astatine, because as the number of electrons increases, the melting point increases. And you know that iodine's a solid. And 3. Cl2 plus 2 NaOH creates NaCl plus NaClO plus H2O. It's very similar. And as the final one, it's like 3 slides, you get a nice jump scare at the end. Analysis of inorganic compounds. I couldn't even find many questions on it. Like I could have made my own, but I didn't want to. You just gotta memorize it. Actually, I could find questions, but they weren't good questions. Right, analysis of inorganic compounds. CO3 minus and HCO3 minus, that's carbonate and hydrogen carbonate. Just remove that as exactly the same thing. Can be added to an acid, and this will produce carbon dioxide. XCO3 plus 2HA, that's a acid, hydrogen acid, or component base, creates CO2 plus H2O plus XA. And to be extra sure that it's like produced carbon dioxide, to make sure it's a actual carbonate, you can collect that gas and bubble it through lime water. You gotta make sure you've got a airtight container. And lime water is just CaOH2, calcium hydroxide. And if it's CO2, then the lime water will turn cloudy, since that limestone has produced CaCO3. I think that is actually. And SO42 minus sulfate ions are tested by using acidified barium chloride, and that will react with the ions to form a white precipitate of barium sulfate. NH4 ions, ammonium ions, when warmed with sodium hydroxide, they'll produce ammonia gas. This can be held to a damp red litmus paper, which will turn blue. Litmus paper. Use red litmus paper and it turns blue in base, and blue litmus paper it turns red in acid. It's got to be damp so that the gas can dissolve, otherwise the hydroxide ions won't be detected. And to test for ammonia gas, you can also use a glass rod dipped in concentrated hydrochloric acid, and if it's a positive result, it will give off white fumes of NH4Cl. That's ammonium chloride, and that's white. Yeah, the jump scare. My character. Thanks for watching. This took too long to draw because it's like a really bad drawing, but thank you, bye. And ask me any questions in the comments, obviously.